Hello, everyone. Welcome back to the AAS YouTube channel. And this is the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Hidetoshi Sano with us today. Hi, Hidetoshi.
Hi.
What is your geolocation? Where are you at?
I'm now staying my home in Chiba Prefecture, close to Tokyo in Japan.
Mm-hmm. Very good. Very good. And let's see. Still winter there. Is it cold?
Yeah, a little bit cold.
Okay.
But I'm using the heater, some heater.
It's okay. Okay, so you got a heater and a sweater going. Very good. Very good. I'm here in Phoenix, Arizona today, and it will probably be low 70s. It'll hit a low 70 F today, which I could convert Celsius real quick if I wanted to, but we'll go. So very good. Hidetoshi, what do you like to do for research? What do you like to do for research?
Very interesting. I love research. So I'd like to know the strong relation between the universe and our human beings. So when I was a junior high school student, so I read the very interesting book. So the book showed the life cycle of stars.
Yes.
So all of element, so without hydrogen or helium or a little bit lithium, are generated within the life of stars. So star formation and inside the stars and the supernova explosion. I surprised. So I decided I will reveal a strong connection between the universe and our human beings. So spend my life.
Very cool. Very nice. I like that philosophy angle to it. So that'll take us to this really lovely article. Pull this up. So this is going to be ALMA CO observations of supernova remnant N63A in the Large Magellanic Cloud, the discovery of dense molecular clouds embedded within shock-ionized and photoionized nebula. And Hidetoshi, take us away.
Okay, so thank you very much. So for giving me this opportunity. So I'd like to introduce this paper first. So we observed CO120 and 322 emission line toward the N63 supernova remnant in the Large Magellanic Cloud using Atacama Large Millimeter Submillimeter Array, so-called ALMA, and Atacama Submillimeter Telescope experiment, ASTE. So we revealed dense and shock interacting molecular cloud toward the center of the supernova remnant. So this region is also known that the hole-like structure of soft band X-rays. So we detected the shocked dense materials in front, but interacting with the shocked supernova. Yeah. So also very interesting. So this dense molecular cloud is associated with the shock-ionized gas traced by optical emissions. So we detect the very nice or rare case. So because the cloud is now destroying by the shock interaction.
Okay.
Very rare case. Yes.
Cool.
Yeah. So we analyze X-ray spectroscopy. So then we revealed shock and cloud interaction also enhances the magnetic field. And we can detect the very strong synchrotron X-rays, or shock cloud interaction also enhances the many reflected shock. So many reflected shock heated up the gas into the high temperature. Yeah, and also these dense molecular clouds play a significant role at the target of the accelerated cosmic ray protons. So cosmic ray proton is very efficiently accelerated, very high energy particle Yeah.
Yep.
So
Yep.
then, so cosmic ray proton interact with cloud, then so we can detect the gamma rays. Yeah.
Very cool.
Yeah. Perhaps future gamma ray observation can reveal the shock acceleration of the cosmic rays in this superenvironment. So it is very many physical contents. Yeah.
Very good.
Thank you very much.
Should we go ahead and slide down? Okay. Anything you want to say? So let's go ahead and, oh, looks like we got the table of the observations here.
Yeah.
Okay, older ones. Okay. All right, and let's go ahead and take a look at figure 1. Go ahead.
Okay. So figure it showed the 3-color image of N63A, so obtained with Chandra X-ray. So in the left panel, so red is 0.3 to 6.0 kilo electron volt, and the green is 0.6 to 1.1, and blue is 1.1 to 6.0 kilo electron volt. So you can clearly see nice shell-like morphology with the hole-like structure towards the center of the supernova remnant. So you can see the black regions. So this region shows the very low intensity of the soft band X-rays, as well as middle band X-rays in green or red or something. So previous study showed that this hole-like structure was created by the interstellar absorption due to the dense gas materials.
Okay.
But the previous study could not find the dense molecular cloud throughout this region. Okay, so and the middle panel showed radio continuum 3-color images. So red is 2.1 gigahertz and green is 4.7 gigahertz and blue is 8.6 gigahertz. Yes. So you can find the central region is very bright. So this was caused by the photoionized gas. Yes.
Okay.
So free radiation. Yes. And light panel showed the radio continuum image superposed on the polarized vectors. So yeah, we find a very small polarized fraction toward this supernova remnant. This is curious. So because the young supernova remnant shows a very high value of the polarized emission. But perhaps so this supernova remnant is also located in, perhaps this was due to the location of the supernova remnant, I think. This remnant is located within the dense H2 regions. So perhaps so this is also affected, the polarized emission, I think.
So the average polarization here is a few percent?
Yeah, exactly.
Okay.
It's very yeah.
Okay. All right, on to figure 2.
Yeah. So figure 2, the large-scale view of the molecular cloud distribution toward N63A. So left panel shows the CO322 emission line superposed on the Chandra X-ray contours. So we have revealed 3 giant molecular clouds toward northeast region and east region and toward west region. So superposed on the dense molecular clouds. So we can clearly see this W cloud is nicely spatial correspondence with the hole-like structure of X-rays. I'm very surprised. And the middle panel shows the H1 image superposed on the X-ray contours. So, owing to the modest angular resolution of H1 obtained by ATCA survey, so we could not resolve the spatial morphology of H1. But we can find a very low intensity level toward the supernova remnant.
Okay.
Yeah. And the right panel shows the enlarged view of the H1 toward the northeast region, superposed on the CO contour in magenta and white contour by the Chandra X-rays. So you can clearly see perhaps the molecular cloud is contacted with the supernova remnant in the northwest and east, I think. So this region also the intensity boundary of the H1 gas. Yeah.
I see.
Mhm.
Yes.
But the angular resolution is modest.
Yeah. It's ALMA, so let's see. Oh yeah, these are the CO J equals 3 to 2 transitions. Okay.
Yeah, exactly.
Okay. Blow that up for people. Okay. Figure 3.
Okay, figure 3. So figure 3 shows the average line profiles of CO 322 inlet and H1. So blue and cyan towards supernova remnant N63A. So we plotted the H1 profiles by blue and cyans. So blue indicate the blue spectra was extracted within the radius of 30 arcsec. On the other hand, so profile was extracted outer region of the supernova remnant. So outside of the supernova remnant. So we can clearly see the towards the supernova remnant H1 spectra shown by blue line. So we can find a very narrow deep-like structure and a negative intensity. So indicating that, so this negative intensity caused by the H1 absorption effect. So perhaps due to the strong radio continuum emission from the supernova remnant, so foreground H1 gas. So some of the associated with supernova remnant and some of the not associated with supernova remnant can be observed by absorption line.
Okay. Yep.
So then, so perhaps the part of this velocity range are associated or just in front of the supernova remnants, we thought. And the CO showed about 200, about 85 or something. Kilometer per second.
Yeah, around there. Yes.
Yeah, slightly shifted. Yeah. Okay.
And the dashed lines were the range of integration?
Yeah, exactly.
Okay.
Yeah.
Okay. I'm with you. Very good. Okay. Detailed CO.
Yeah.
All right. Ooh, that's a pretty picture. I like that one. Very nice. Beautiful.
Yeah, thank you. So this is a 3-color image of the N63A. So this is a real image. So red shows the H alpha obtained with Hubble Space Telescope, and green shows ALMA CO, and blue shows the Chandra X-rays. So thanks to the ALMA very high angular resolution, about 3 arcsec, so we resolved the clumpy CO structures, associated with supernova remnants. Yes, 3 parsec is here, and ALMA resolution is very small.
Yes. How old is this supernova remnant?
Yeah, exactly. Yeah.
How old is this supernova remnant?
Oh, how old? Oh, yes. So this remnant is about 5,000 years old.
Okay. Okay.
Yeah. So this is very surprised. So molecular cloud complementary distributed with H alpha emission. So H alpha emission can trace the ionized gas.
Yes.
Yeah.
Very nice. Cool. Very cool. All right. And figure 5.
Yes. So this is the enlarged view towards optical nebula of L63A. So color image shows the 3-color composite. So red is S2 line emission, and the green is H alpha, and the blue is O3. And the superposed contours indicate ALMA CO. Yes. So this is very interesting. So first impression is toward the cloud ABC. So you can find dark lanes nicely associated with the cloud ABC, ABD. So suggesting that these clouds are a little bit in front of the this optical nebula.
Yeah. Okay. Mm-hmm.
You can find very bright lobe, optical lobe in the left side, only left side shell. So this region shows a very high intensity ratio of the S2 over H alpha, suggesting that so these ionized gas was originated by shock ionization.
Mm-hmm. Mm-hmm.
On the other hand, the right side panel, right part is not so high intensity ratio. So suggesting that so this was formed by photoionization.
Mm-hmm. Photoionization. Mm-hmm.
So this is very interesting nebula. So left side shows the shock ionization, but the right side shows photoionization. So if you look at the exciting star in the right hand, right part, so you can find the pillar-like structure, uh, like such as the dark rain-like structure. So
Yeah. Okay.
yeah,
Okay.
yes, yes,
And then these various letters are indicating features.
yeah, exactly.
Okay. Okay.
So some of the left panel molecular clouds was evaporated by shock interaction. Then, so we can find a very small cloud I and J or H. But the light part, so cloud A and DB,
Yeah.
are very dense. So then, so which survived by shock erosion. But now ionized by exciting star. So due to strong UV radiation.
Okay.
Mhm.
Okay. I'm good. I'm good. And properties of the cloud. Here we go. Here's A to K. And we have various properties of those clouds embedded within the supernova remnant. Yes. Okay. A to F was photoionized. G to K was shock-ionized. Let me go back to here. Shock, 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 shock.
Yeah.
Photo. Interesting. Looks like that. Okay. Mm-hmm. Mm-hmm. Density goes up. Yeah. Okay. Very cool. Ooh. Okay. Figure 6.
Yeah. So figure 6 shows the three-color image of SNR N63A obtained by Chandra. So color images are similar to the previously shown. So because red shows the open 3 to open 6, and green shows open 6 to 1.1, and blue shows the 1.1 to 6.0 kilo electron volt, respectively. Yeah, and the superposed contours are different. So for the panel A shows the H alpha, and B shows the S2, and C shows the O3,
Mm-hmm.
and D shows the ALMA CO, and the panel E shows the radio continuum, and the panel F shows the boundary of the H alpha radio continuum and CO. So in this picture, so we find that very interesting point. So for example, the O3 emission shown at the panel C. So O3 traces the shock to regions.
Mm-hmm.
So you can find some of the part of X-ray bright part show the very bright O3 emissions. So as well as the light dense part has no bright X-ray emissions. That's interesting. And we realized that in panel D, so CO cloud is not entirely located toward the hole-like structure of the softband X-rays.
Right.
So this is a very important point. So yes.
Yep.
And figure F is very interesting. So okay. So if we combine the ionized gas traced by using the radio continuum and the optical emission and the CO emission. So CO emission can trace the neutral molecular hydrogen. So then we can trace, or you can, so the field coverage is much the softband X-ray hole-like structure. That's interesting. But some of part of the southern part, so southern part of hole, so there is no counterpart. Is optical ionized emission and radio continuum ionized emission and molecular cloud. So perhaps some of missing interstellar medium is located. For example, the H1 gas, cold H1 gas, or CO dark molecular cloud. Because the shock interaction destroys the carbon monoxide molecule into the C and O. So perhaps some of the neutral carbon is associated towards this southern part of the hole-like structure, I think. So I will propose the C1 observation toward this source in the next ALMA call for proposal.
Okay.
Yeah.
Good. All up. Okay. Go ahead and slide the origin of hard X-rays. And figure 7.
Yes. So this is a result of the X-ray spectroscopy. So X-ray data were extracted toward the northeast region and west region and southeast region, as shown in previous figure 6.
Right.
Could you go back to figure 6?
It's going to be here is west,
yes,
east, south.
So we noted the dashed polygons in the panel D. So northeast region. So this is a reference position, and the southeast region. So this is a shock ionized regions, and the west region. So this is a photoionized region.
Yes.
So then, we analyzed the X-ray spectra using the model fitting method. So as a result, so the reference region of northeast can be reproduced CIE, ISM plasma, and NEI ejector. So it is very general or normal shock ionized plasma. Yes. So, and also is as well as we can reproduce the CIE and NEI ejector. So on the other hand, shocked gas region southeast is very interesting. So if we fit the CIE plasma, so shocked ISM and the NEI ejector, so we find the residual around 5 kb.
Okay.
Yes, panel C and so yes, residual. Yes.
Yes.
Yes. So then, if we add the power component or high temperature plasma from the ejector, so we can fit the spectra. So this is very important point. So then, we will discuss the origin of the high temperature plasma or hard band X-ray. So these hard band X-rays can be reproduced by both the power law model or high temperature plasma. So I emphasize that these hard band X-rays is strongly related with the shock crowd interactions. So I will discuss later.
Remind me, what does PL stand for?
PL is the power law. So from the cosmic ray electrons. So synchrotron X-ray.
Okay.
Yeah.
Got it. Cool. Okay. All right. Best fit X-ray parameters.
Yeah.
There's the quantitative parts. We got the northeast, the west, the southeast.
It's a very busy table, but so most important point is, so if we add the power law component toward the southwest region, so power law photo index is about 1.7. So it is so flat. But the error bar is very large.
Right.
So yes.
Yeah.
So due to the low photon statistics, we could not fix the value accurately.
Okay.
But as a parameter was fairly good, I think.
Very nice error bars and everything, uncertainty, very good. And then figure 8.
Yes. So figure 8 showed the three-color image. So red showed the Chandra X-rays in the energy band from 4.3 to 6.0 kV. So this energy band is corresponding to the hard tail of the X-ray spectra. So without line emission, so continuum emission. And the greens are ALMA and blue is Chandra X-rays. So we can find the hard X-ray image is toward the peak A regions. So this region is also detected, strongly detected shock-ionized gas. So then, perhaps this hard band X-ray is related with the shock crowd interaction or shock ionization. So on the other hand, we also found some of minor peaks under peak D. So but there is no dense molecular clouds. So perhaps this spot is associated with H1 cloud, I think.
Okay.
So then, I proposed 2 scenarios of the origin of the hard band X-rays. So one is the synchrotron X-rays. So shock and crowd interaction enhances the magnetic field. So then, magnetic field enhances the synchrotron X-rays toward these regions. Or shock crowd interaction also generate many reflected shock. So reflected shock can heat it up the ISM or ejector into the higher temperature.
Okay.
Perhaps future deep observation of X-ray can reveal the origin of the hard X-rays toward these regions. So anyway, shock cloud interaction is very important.
Indeed.
Yeah.
Very nice. And then we end off, I do believe, on this relatively short 14-pager. Very good. So Hidetoshi, where do we go from here, given what you've published? What's the future of this supernova remnant over the, let's say, the next 5 years or so? You mentioned a little bit that there was, new proposals coming, things like that. So where do we go over the next 5 years to help unravel some of the mysteries of N63A?
That's a good question. So I think Cherenkov telescope array, so it is a new generation gamma ray telescope, is holds a key to understand the supernova remnant science. So supernova remnant is thought to be the cosmic ray proton accelerators. So there is no conclusive evidence So that's a very curious.
Yes.
So I think so CTA can resolve gamma ray emission as well as morphology, gamma ray morphology towards the many supernova remnants.
Okay, that would be.
Yeah. So then so we can reveal the origin of cosmic ray protons or cosmic ray acceleration in supernova remnants. So to reveal the cosmic ray origin in supernova remnants, so molecular cloud gas information is very important. So because so gas cloud act as the target of the cosmic ray proton. So then produce the gamma rays. So then so near future, so gamma ray observation is very important to understand the cosmic ray acceleration in supernova remnants. Also, the ALMA C observation is very powerful tool to understand the shocked cloud in the supernova remnants.
Right, which is setting up those.
So I will review the many supernova remnants associated with the interstellar gas using ALMA.
Nice.
Yeah.
Very nice. All right. Hidetoshi, I want to thank you very much for sharing your lovely article with us today. So thank you very much.
Thank you very much.
All righty. And thank you, everyone. And we will see you on the next one. Bye-bye.